We have seen that dynamic programming can be used to determine the optimal policy for a dynamic lot size model. Instead of that, we can also use a heuristic to get a reasonable solution with easier calculations. One of the heuristics that exist is the silver meal heuristic. This heuristic can be used if the variable ordering cost is constant and also identical for all the periods. So there's just the fixed amounts that you pay per product that you order. And that should be constant because this heuristic basically only balances the setup cost and the holding cost. So if that variable ordering cost is then also going to vary, then the performance of this heuristic will not be that good anymore because that is not taken into account. What we are going to do for this heuristic is we will first define TC as a function of I and T, and that TC denotes setup cost and holding costs for the periods I to T, if we order in period I for those periods. So that looks maybe complicated, but the idea is that, or as an illustration, we could say, for instance, that in period 1, we order for period 1 only. So that is TC11. In that case, we only pay the setup cost for period 1. Then you can also choose to order in period 1 for period 2 as well. So then we still pay that setup cost in period 1. And then for the products that we have to store at the end of period 1, we pay the holding cost H1 multiplied by the number of products that we need to store. So here we need to store the demand for product 2, if we also order for product 2. And then next step, cost, if we order in period 1 for periods 1, 2 and 3, it's the same. We have to pay the holding cost for the products in period 2. And for the products in period 3, we pay 2 times holding cost. So first at the end of period 1, and then we again need to pay a holding cost at the end of period 2. And those holding costs need to be paid for the demand in period 3. So what you see is that if you add one more period, then you basically have the same expression, and each time we add one more term. First this is added, and then this one is added. And that basically means that we can also calculate those values recursively. So that's also written over here. We start just with the setup costs, and each time that we add or that we increase this I by 1, and we add one more term. So that's how we can calculate those values most easily. Those are the total cost for these periods. To get a fair comparison, we are then going to divide by the number of periods that we consider. So if, for instance, we order in period 1 only for period 1 itself, then we divide by 1 minus 1 plus 1 is 1. If we order in period 1 also for period 2, then we are going to divide by 2, because then we consider 2 periods. So we divide by the number of periods that we consider, and then we have the cost per period. So that needs to be calculated as part of the heuristic, and then this is how the heuristic works. So we will start with the first periods, and then we are going to add periods until we have found or until we have realized that we have found a local minimum. So maybe the cost period of time is first going down, and then at some point it's going up again. Then we have seen that we were in a local minimum. So, and then we order for all those periods until we have reached that local minimum. So local minimum is basically that the previous total cost per period was higher, and also that the next one is also higher. So then we order for those periods, and then we start from the next period, and then we basically do the same again. So let's apply that to an example. So here we have 6 periods, all with another demand. We also have setup costs that are changing over time. The holding cost is always 1 per unit, except for period 4, there it's 3. And let's then see what we get if we apply the silver meal heuristic to this problem. one more thing is the variable ordering cost is $2 for each period. So it's indeed constant, so that means that we can use this heuristic. So we start with iteration 1. That means that we start with I is 1, and then the question is for how many periods are we going to order in period 1. We will first consider only period 1 itself. So then we have a demand of 10 and we only pay the setup cost. So this is the cost that we then pay, and that you see over here. No holding cost if you only pay for the period itself, and that $20 is then only for one period. So then per period is also $20. If we add period 2 to that, then in period 2 we have a demand of 15. So then you see that you get this 20 again, and then you add the holding costs for those additional 15 products. Those need to be stored at the end of period 1 at a cost of 1. So you have 1 times 15, and that's what you add over here. Then we get 35, and then the cost is going down to 17.5. We can then also add the third period. There the demand is 7. If we are also going to order those 7 items in period 1, then we need to store those items 2 times. 2 times at a cost of 1. So that's 2. The 1 plus 1 is then multiplied by 7, and then we get 49. The 49 is for 3 periods. So per period the cost is 16.33. And we are still looking for a local minimum. So if we also add the 4th period, so if we then also order for those 20 units already in period 1, then you see that we have to pay a holding cost 3 times. That is then also added. So again, we start with this 49, and then we just add the holding cost for the additional periods that we add, and then we will find 109. If you divide that by 4, then you get 27.25, and then you see that it's now going up again. So this is the local minimum. That means that in period 1 we are going to order for periods 1, 2 and 3. That's what the silver meal heuristic describes us to do. And then the next iteration starts in period 4. So then we continue with iteration 2. We have a demand of 20 in that period, and we have a setup cost of 18. And then the cost per period is 18. We also see over here that if we store something at the end of period 4, that's quite expensive. So in period 4, if we also order for period 5 there, then you see that we add 3 times 13. So 3 times the amount that we need for period 5. And then the cost per period is immediately going up. So that means that we have now immediately found a local optimum. That means that in period 4, we will only order for period 4 itself. And then for iteration 3, we continue from period 5. Then basically the same idea. It's better to only order for period 5 itself. Also because the demands in period 6 is quite high. So if you also need to order those, then the cost is going up. So in period 5 we only order for period 5 itself. And now you see also that this is heuristic, that the performance is sometimes maybe not that good, because now we also need to order in period 6 for itself. And in period 6 we have quite a high setup cost, so that now also needs to be paid. So this is definitely not the optimal solution, but that's what you have if you have or if you use a heuristic. So in period 6 we order 25 units. So let's summarize the solution that we get. If you apply the silver meal heuristic, then we get that we order 32 in period 1. That's for all the periods 1, 2 and 3. And then in periods 4, 5 and 6 we are going to order 20, 13 and 25. And then the total of the setup and holding costs equal $122.